Okay, kids. So we are going to start Lagrange mean value theorem today. In the last class, we have studied about Rolle's theorem, and what Rolle's theorem says that. Then we have done work on Rolle's theorem. Okay. So let's get started with Lagrange mean value theorem, and we call this LMVT in short. L for Lagrange, M for mean, V value, and T for theorem. Lagrange mean value theorem. Is that clear? So let's start with the statement or the theorem. What theorem says that? Let f be a continuous function in closed interval a to b and differentiable on open interval a comma b, then there exists at least one c belongs to open interval a comma b such that f of b minus f of a is equal to f dash c b minus a. Likewise, in the Rolle's theorem, there were three required conditions. What were they?
Continuous,
First, continuous in closed interval and differentiable in open interval. And third one was f of a must be equal to f of b in the case of Rolle's theorem.
Yes.
What is the necessary and required condition for Lagrange mean value theorem? Point wise, let's understand it by point wise way. Point wise, if we go, it says that first, what it is required? Continuous for all x belongs to the domain a to b, close interval a to b. And second requirement is differentiable for all x belongs to open interval a comma b. So these are the two main conditions required for this LMVT. And if these two conditions are met, then Lagrange says that there exists at least one c. There exists at least one c belonging to a comma b, open interval a comma b, such that f of b minus f of a is equal to f dash c times b minus a. If these two conditions true, then there exists at least one c belonging to open interval a comma b such that f of b minus f of a is equal to f dash c times b minus a. This is what Lagrange theorem says. Any doubt in this statement? You already learned the theorem. Just note it down. Clear? Let's understand it by geometrical meaning, have geometrical significance of it. Just draw a figure of function y equal to fx as shown here. Just draw a function y equal to fx and x-axis and y-axis. On x-axis, we are plotting a and b. So let's say at point x equal to a, the value of the function is f of a. So you can say that, let's say this is a point a. So coordinate of a must be a comma f of a. Is that clear? Is that clear?
Yes, sir.
Now b, let's say b is a point on x-axis, and at b, let's say x equal to b. At x equal to b, the function has value f of b. So capital B is a point on the function, on the graph of the function y equal to fx, and name it b comma f of b. Is that clear? Now let's draw a second passing through A and B. Let's draw a secant. This is what we call secant. Passing through point A and B. Can we have slope of secant AB or straight line AB? Slope of AB is equal to, can anyone tell me what is the slope of AB? Slope of line, if there are 2 points is given, y2 minus y1 upon x2 minus x1. So in place of y1 and y2 is f of A and f of B. So slope of AB become f of B minus f of A
by B
upon B minus A. Is that clear? Now let's understand the theorem again geometrically. What it is saying, fx is continuous in closed interval A to B and f is differentiable in open interval A comma B. Then there exists at least one C belonging to open interval A comma B such that, look, we have a relation like this such that f of B minus f of A equal to f dash C B minus A. This can also be written as f dash C is equal to f of B minus f of A upon B minus A. And what it is? This is m of AB. AB line. Is that clear?
Yes, sir.
So f dash C. So what it is telling if function is continuous in closed interval A comma B and differentiable in open interval A comma B, then there exists at least one C belonging to open interval A comma B such that f dash C is equal to the slope of the line AB. It means that there might be some C where the differentiation equal to the slope of the line AB. Now, what does this f dash C imply? It implies that the differentiation or the slope of the tangent at x equal to C, f dash C is equal to dy by dx at x equal to C, or slope of tangent at C at x equal to C. Is that clear?
Yes, sir.
This is slope of the tangent at x equal to C. So there might be some C in between A and B, where tangent is parallel to this line segment AB. Why it is parallel to? If two lines are parallel, then their slope must be equal. So we know f dash C is equal to slope of the line. So there might be some C where tangent on the line becoming parallel to the AB line. So this is the C. So now what is LMVT? LMVT is if function is continuous on closed interval, differentiable on open interval, then there exists at least one C on the curve y equal to fx where tangent become parallel to the slope of become parallel to the line segment AB. Any doubt?
Yes. No, sir.
No. So let's understand by an example. Let's solve it. And you can see here, it is not requiring any situation like f of A equal to f of B. It's not a necessary condition. If it is, if f of A equal to f of B, that become a special case of LMVT. So Rolle's theorem can be derived from LMVT.
Yes, sir.
Okay. Now, let's have an example. Let's solve it. Question is, verify mean value theorem for fx equal to this on closed interval minus 1 to 2 by finding C. So how to solve such kind of problem? How to verify LMVT? So let's solve it. So what we know, fx is a polynomial function.
And con-
Polynomial function. So it is continuous
and differentiable.
Continuous for all x belongs to close interval -1 to 2. First statement verified, LMVT first statement. And second,
F of
fx is also differentiable. Why it is? Since it is a polynomial function, is also differentiable
for all x belong to.
For all x belongs to open interval a comma. So now these two conditions, that is minimum required condition for LMVT, has been true. Now we need to verification statement. Now what it is saying, that if these two conditions are met, then there exists at least one C in between -1 to 2. We need to write -1 to 2 here. There exists at least one C in between this, such that f dash C become equal to the slope of line segment AB. So what we are going to have, first of all, m of AB slope is f of B minus f of A upon B minus A. We are going to find this. Okay. So this implying f of B become 2 minus f of -1 upon 2 minus minus 1. Is that clear? So how much we are getting? F of 2 become equal to 2 square is 4 minus 2 is 2 plus 1 3 minus, what is the value of it at -1?
3, sir.
It is 3 upon 3. It is 0. It means that there must be at least one C where f dash C become equal to 0. So this is f dash C equal to 0. So we need to find C. So this implies what we are going to do is we are just differentiating fx. F of x is equal to
2x minus 1.
2x minus 1, and let it be equal to f dash C. F dash C become equal to 0. So x is equal to 1 by 2, and this is what we are talking about C. This is what we are telling, this is C. Is this C belongs to -1 to 2? This is belonging to -1 to 2. This implies LMVT is verified. Any doubt, kids?
No, sir.
No. So this is how we solve LMVT problems. Let's move on to another question. Solve it. Find C of the LMVT for the function fx equal to 3x square plus 5x plus 7 in the interval, close interval 1, 3. Solve it. Write it down. LMVT is also one of a kind which is most asked in the exam. This is as important as Rolle's theorem it is. Is that clear? So you need to work on it. Are you getting C? solve it. What we'll write here first point, fx equal to fx is a polynomial function. Nomial function. Hence,
It is
continuous
for all x belong to
for all x belongs to whatever it is given.
closed interval 1 to 3.
1 to 3. Okay. Now, second, since f is a polynomial function, so it is differentiable to fx is differentiable for all x belongs to open interval 1 comma 3. Now minimum condition required for LMVT, hence minimum condition required for LMVT has been met. Now we need the verification round. So we are going to verify what it is. There exists at least
one C
belonging to open interval 1 to 3 such that f dash c become equal to f of 3 minus f of 1 upon 3 minus 1. Is that clear? So f dash c is equal to what it is? F of 3, how much?
49
3 square plus into 3, 27 plus
49, sir.
It is 49, let's say.
Minus 15.
Minus
15
by
2.
By 2. So how much it is?
34 by 2, 17.
17. So now question is what? We need to find c, na? So we are going to differentiate the function f dash x
6x plus 5.
6x plus 5 and it is equal to 17. Now you can see 6x is equal to 17 minus 5 is 12 and x is equal to 2.
2. Yes, sir.
This is what we are telling c, and 2 belongs to 1 to 3. So hence we got 1 c. It is talking about at least 1 c. So if you got at least 1 c, then it's verified. This implies LMVT verified. Any doubt, kids? No, not at all. So what is the LMVT? Lagrange mean value theorem. What it says that function is continuous in closed interval, first condition. Yes, second condition, it is
in open interval.
Differentiable, yes, in open interval. Then
there exists a point C where
then there exists at least 1 point.
Yes, sir.
Then there exists at least 1 point C in between open interval such that f dash c become equal to the slope of the line. Is that clear?
Yes, sir.
So this was LMVT. Solve this question, do it fast. In closed interval 0 to 1, LMVT is not applicable to. You need to find in which condition, for which function out of these given 4 options, LMVT is not applicable. You need to find those functions where LMVT will not work. Solve it, kids. Let's check one by one. Let's check it one by one. What can we say about A? Is it continuous in closed interval 0 to 1? So this is a polynomial function. This is also a polynomial function. So it must be continuous in their domain. Where it might be the problem? At half. So we'll check continuity at half. You can see f of half minus how much it is? It is coming out to be 0. And f of half, it is also 0. So it is continuous at half as well. It is continuous at half as well. So first condition for continuity for this function has been met. Now what we need to have? We need to have differentiability conditions. So main problem occur differentiability at half. So what we will do? We will have f dash x, just have a differentiation of it. Since it is continuous, so f dash x can be written as minus 1 for x less than half. And how much it is? 2 1 by 2 minus x into minus 1 for x greater than equal to half. So what about f dash half? You can see for the minus, this is minus 1 and it is coming out to be this is minus 1. So sorry, it is minus 1. 2 times 1 by 2 minus x to the power 1 into minus 1. You can see it is not differentiable. Is that clear? For this, it is getting minus 1. At here, you can see it is coming out to be 0. It's not differentiable. So will LMVT applicable in this case?
No, sir.
Basically, we need to find f dash half using first principle. Here, f of x minus f of half upon x minus half. Is that clear? But the earlier method we have, I have given a short trick so that you can apply that one in competitive exam while objective session is there. And this is the method that you need to apply if you are doing in board kind of exam. So what it is? Here you can see f dash, you need to find f dash half plus right hand derivative RHD. Since functions are different in different cases, RHD. So you can see f dash half plus become 1 by 2 minus x to the power 2 minus f of half is 0 upon x minus half. So what are you getting here? It is x minus half limit x tending to 1 by 2 plus. So it is x minus half and it is coming out to be 0. Right hand derivative is 0. Now what about left hand derivative? Left hand derivative f dash half minus limit, you need to find right limit 1 by 2 plus limit x tending to half minus will be written as, for half minus the function is 1 by 2 minus x and minus f of half is 0 upon x minus half. So you can see this is coming out to be minus. So left hand derivative and right hand derivative is not equal. So we will say that f dash half does not exist. Means function is non-differentiable at half. So will it LMVT is applicable or not? Is LMVT applicable or not? No. So this is the answer. LMVT is not applicable to this. Now let's move on to another part, B. What can you say about B part? Solve it. Now f dash 0, you need to find f dash 0. F dash 0 become equal to limit x tending to 0, f of x minus f of 0 upon x minus 0. This is first principle. It is continuous in this interval. Continuous in this interval, you can see we need to check only differentiability. So limit x tending to 0, fx is sin x upon x, minus f of 0 is f of 0. You can see this is 1 upon x. Any doubt here, kids, girls?
No, sir.
Do you remember this first principle? Have you remember?
Yes, sir.
So we are applying on that only. And you can see this is limit x tending to 0, sin x minus x upon x square. X square. Limit x tending to 0. What is the expansion of sin x? Can anyone tell? X minus x cube by 3 factorial plus x power 5 by 5 factorial minus and so on, minus x upon x square. Even we can apply L'Hopital rule as well, or we can directly say that this does not exist, or you can say, you can see here limit x tending to 0, and this is minus x by 3 factorial plus okay. Please have a check. Is there any doubt? Is there any problem with differentiability of function at 0? This is what we are having. Expansion of sin x, x minus x cube by 3 factorial plus x power 5 by 5 factorial. It's alternate, plus minus x. So what we are getting, we need to divide it by x square simultaneously. So we are getting x minus 3, and this is x to power 3 by 5 factorial minus and so on, and this is coming out to be 0. So function is differentiable at x equal to 0, you can see. So Rolle's theorem will be applicable on this function. What I was thinking that it will not be, but you can see from the theory, it is saying f dash 0 is 0. Any doubt, kids?
No, sir.
Let's show you some graph so that you can have clear understanding of what is happening here. Let's show you some graph of sin x upon x. Are you getting it?
Yes, sir.
Okay. So we are going to plot the graph of y is equal to sin x upon x. Can you see? This is very smooth function here. You can see sin x upon x function is very smooth at x equal to 0. This is at x equal to 0. So it's differentiable. Any doubt, kid? Any doubt? It's differentiable and it is continuous too in 0 to 1. So Rose's LMVT will applicable in this. So is this the answer? No. Now what about C? Can anyone tell me? Will LMVT work for C section, C option?
Sir, for C it is applicable, sir.
It is applicable. How do you know that? We are not applying, we are just plotting the graph. Now if we know the graph of the function, then it is very easy for us to say that it will LMVT will applicable or not. You can see the domain is from 0 to 1. Let's say this is 1 here and this is 1. So you can see from 0 to 1 it is very smooth curve.
Yes, sir.
And LMVT will apply here. It is continuous everywhere and it is smooth, so differentiable in 0 to 1. So this is also not the answer. What about D? What about D? D section?
It's not applicable, sir.
Why it is so? You can see the graph of y equal to mod x 0, 0 to 1. What is our domain, kid? Girls, what is our domain? Domain is 0 to 1, na? So we need to check only from here to here. And from here to here, function is only this. Only this is the function. For that straight line, function is continuous in 0 to 1. It is differentiable too. So LMVT will applicable in this function.
Okay, sir.
Okay, so this is not. So A is the only correct answer for this question. Any doubt? Let's move on to another part, another question. Solve this question. A value of C for which conclusion of LMVT holds for the function fx equal to ln x on the interval 1 to 3 is. There are 4 options A, B, C, and D. So you need to find C. Solve it. Do it fast. Solve it, solve it. A value of C for which conclusion of LMVT holds for the function fx equal to ln C in the interval 1 to 3 is. Tell me the answer if you know, if you can solve it. What is the domain of ln x? Can anyone tell me domain of ln x?
Sir, the option is C, sir.
Are you getting it? Have you got the answer?
Yes,
Domain of ln x is 0 to infinity, but we are talking about 1 to 3. So function is continuous. Logarithmic function are continuous in their domain and differentiable too. So what we need to find? We need to find C is equal to f of 3
of 3
minus f of 1 upon 3
2.
minus 1. We need to find.
3
So
minus
what is f of 3? This is ln 3 minus
ln1
ln 1 is 0. Upon 3 minus 1 is 2.
2.
This is f dash c. Now what we need to have is, we need to find f dash x, that is 1 upon x. This implies f dash c become equal to 1 by c, and this is equal to ln 3 by 2. Is that clear? So c become equal to 2 upon ln 3. This can be written as 2 log e to the base 3. How is it? We know log a to the base b is equal to 1 upon
1 upon log
b to the base a. This is a formula.
Yes, sir.
Any doubt till now?
No, sir.
C is the correct answer for this question. Now, let's move on to another concept. Just have a look of it. Okay, we have one more very important concept, and you need to understand it and what it is saying. Sometimes it's required to prove the inequalities, proving inequalities, and based on LMVT. And what it is? So we know the statement of LMVT. It is f dash c equal to f of b minus f of a upon b minus a for y equal to fx for all x belongs to closed interval a comma b. Is that clear?
Yes, sir.
Now c lie between open interval a comma b.
Yes, sir.
So there might be some x where f dash x might be achieving their maximum value, and there might be some x where f dash x achieving their minimum value. So can we write this statement that f dash c always lie between
Sir.
f dash x min and f dash x max. Is that clear?
Yes, sir.
Is that clear?
Sir, we actually have another class.
Yeah, no issue, but just 1 minute. Okay.
Okay,
This
sir.
is done. Okay, so what is f dash c? F dash c is f of b minus f of a
Of
upon
by
b
b
minus a.
minus a.
So we have the concept here. F dash c equal to f of b minus f of a upon b minus a times this number always lie between f dash x min and f dash x max. Any doubt in this part?
No, sir.
So basically statement is this. The statement is this. You need to understand it. Just have a note and work on this concept. Okay. There are some few questions based on this. You can have try at home. This is the first question. Let f be a continuous in closed interval 1 to 3 and differentiable in 1 comma 3. Suppose that for all x belongs to open interval 1 comma 3, 1 less than equal to f dash x less than 2. Prove that this is the basic example based on the theorem. This is second question, and this is third question. So these are 3 questions that you need to work at your home. Okay, kids, we'll meet you next session.
Thank you, sir.